All right, so in our previous lectures, we've been talking about mole balances, and one of the reoccurring themes is that we are basically designing reactors by writing mole balances structured around the rate law for some reaction. So we want to carry out a reaction, and we want to design a reactor to do that. To do that, we need to know something about the rate law, and so then we incorporate this rate law into the mole balance, and we can use that to design a reactor. So in this lecture, we're going to get into more on how that rate law is constructed. Chemical reactor design is the process of designing reactor systems around chemical kinetics. As we study chemical reactor design, we aim to see how different types of kinetic scenarios influence reactor design decisions. Derivation of rate expressions is not at all straightforward. So doing this for even one reaction could extend over multiple PhD dissertations or decades of industrial work. So when we look at these rate expressions, these rate laws, we're really taking them for granted. There's a lot of work that goes into figuring out what those are. And to be honest, that is not part of this class. This class is not focused on deriving rate expressions for reactions. In this class, we are interested in understanding how common rate expressions influence reactor design. Often simplified forms of the rate expressions, the ones that we use, they provide nice estimates for reactor design. So you'll see this in this class, and you'll also see it when you take process design. So we'll get into some more detailed rate expressions later in this class, specifically when we study catalysis. We'll get a taste of how the rate expressions that we see are developed based on mechanisms. Even when we do that, the mechanisms that we will look at will be very simplistic, and they are also being used as surrogates for the actual models and work that goes into deriving mechanisms and rate laws. So just keep all of that in mind. There's a lot that goes into developing rate laws and the mechanisms that underlie them, but at the end of the day, the simplified expressions that we use here can tell us a lot in terms of reactor design. So all of that said, talking about rate laws. So a rate law is a model. So a model is something that's used to simulate or model the behavior of something. So a rate law is used to model how the net generation of a species, of a chemical species in a chemical reaction, changes due to changes in concentration and temperature. So the rate law dependence on temperature, we'll see that in the next lecture. In this lecture, we'll focus on how the rate can be modeled in terms of concentration. The concentration dependence of a chemical reaction can often be modeled using a power law model. For example, if we take our generic reaction here, A plus B goes to C plus, or A plus B goes to C plus D, and we assume that this reaction is irreversible, one way that we could model the rate would just be to say that for example, the rate of consumption of A is equal to some rate constant times the concentration of A to the N power times the concentration of B to the M power. So I haven't given any details on what N and M are, but basically what I mean by a power law is we take the species that contribute to the reaction. This is an irreversible reaction, so the only species that contribute to the reaction are the reactant species. And so I take the concentrations of those species and I raise them to some power. The N and the M are exponents. There's really no limit on what N and M could be. They could span from negative infinity to positive infinity. They don't have to be positive. They don't have to be integers. So they can really take on a lot of different values. A case that we look at often in this class is the case of an elementary reaction. So a specific case where the reaction is elementary. So this means that the rate law is essentially a product of the rate constant times a function of the products of the different concentrations of the different species that participate raised to their stoichiometric power. So in other words, I have a rate constant, K, in this case A, and that's the function of temperature, which we'll get to in a future lecture. And then we multiply this by a product of the different concentrations of the participating species. So we'll say we're just going to make a product over I, and in an irreversible reaction, we'll make the product over the number of reactants, Ci, to the nu I, where recall from the last lecture that nu stands for stoichiometric coefficient. So basically, this is a product of the concentrations of the participating species raised to the power of their stoichiometric coefficient. So if we go back to our example, A plus B goes to C plus D, then the rate law would be, in this case, Ka, function of T, Ca, Cb. So in this reaction, the stoichiometric coefficients on both A and B are 1. So here in this power law model, I set these stoichiometric coefficients of both these, of the concentration of A and the concentration of B, both to 1. And I do that because I've made the assumption that the rate law is elementary. So let's do another example. I have this reaction here, the nitric oxide oxidation reaction. This so happens to be the reaction that I spent 5 years thinking about during my PhD. So this reaction here is elementary, or at least in this example it is. So what is the rate expression? So in this case, I'm going to do the exact same thing I did in this last example. I'm going to write a power law, and I'm going to set the exponents of the reactant species to their stoichiometric coefficients. So I'm going to say our NO is equal to K NO function of T CNO squared CO2. So the concentration of oxygen to the first power and the concentration of nitric oxide to the second power. So two important notes about this. So one, if you're told that a reaction is elementary, take that to mean that the reaction is elementary as written. So in other words, do not alter the stoichiometry of the reaction and then write the rate expression based off of the altered stoichiometry. So in this example, the nitric oxide oxidation reaction, the stoichiometry as given is 2 moles of NO reacts with 1 mole of oxygen to form 2 moles of NO2. It sometimes is convenient to reduce this stoichiometry, divide everything by 2, and get this stoichiometry. 1 mole of NO reacts with half of a mole of oxygen to form 1 mole of NO2. And in chemical sense, if we were writing out a chemical equation for chemistry, that's fine. But if you're given a reaction with one stoichiometry, and then you're told that the rate law is elementary, you have to use that same stoichiometry that you're given. You can't alter the stoichiometry and then write the rate law. If you do that, you are using different kinetics than the person giving you this information intended for you to use. So either the textbook or me, we gave you a reaction stoichiometry, and we assumed that you would just use that reaction stoichiometry as is and convert, and then create from that a elementary rate law. We did not say first reduce the stoichiometry and then create a rate law. So that's one of the biggest sets of confusion that students have in this unit, I've found. And really, when you do that, you're making it more complicated on yourself. So bottom line here, if you're given a reaction and told it's elementary, it means it's elementary as written. Okay, so that's point number one. Point number two about elementary rate laws, if you're working a homework or exam problem in this class and you aren't given information about a rate law, you can simply assume that it's elementary as written. So in that case, you would write down, assume the rate law is elementary. So write that down as part of your solution and proceed on with your solution. That is perfectly acceptable. That is an excellent way to get an estimate of the rate law when you don't have any other options. Okay, so moving on. Another type of rate law that you'll get in this class is an nth order reaction. So sometimes you'll be told the reaction is n order in A, or simply the reaction is n order. So what this means is that your rate law, the exponents in your rate law are going to sum to n. So for example, your rate law would look something like this. Ka of t. Again, you're going to have this power law model, so a product of concentrations. We'll say number of reactants or relevant species. And then concentration of the different species, and we'll say, and this time instead of nu, we'll use n, where ni are the reaction orders. So they're more general than the elementary case. And in this case, there is a requirement that the sum over I of ni must equal n. So if it's a second order reaction, then the sum of the different n values must equal to 2. If it's a first order reaction, then the sum of the different n values must equal to 1. Oftentimes when you're given it's an nth order reaction, it tends to imply that the reaction orders are integers, but it is not necessarily the case. Often when the kinetic information is given in this way, it means that the rate expression only depends on the concentration of one component. So if you're given a very general expression like this, the reaction is n order, that usually means you only need to worry about one component. Now, if you're told the reaction is n order in A, that means you probably only need to worry about A. And if you're told the reaction is n order in A and m order in B, well, of course, you need to worry about both A and B. If you're given the very vague instruction, the reaction is n order, that usually implies that it's n order in one component. So it doesn't mean, okay, I have 3 reactant species and the reaction is first order, so they're all going to contribute some fraction of 1 to the rate law. It usually does not mean that. Usually it means pick one of those reactants and it's first order or whatever in that reaction. Okay, so knowing that, let's do some examples. The first, the reaction A plus B goes to C, and you're given the information the reaction is first order in A. How should I write my rate law? So in this case, my rate law would be minus RA equals KA CA. So the reaction is first order in A. I have 2 reactant species here. I'm not given any information about B. I'm just told it's first order in A. So I'm just going to take what the problem tells me and write that down. Let's look at another example. So in this case, we have this compound, CH2OCH2 plus H2O goes to this compound, which I believe is ethylene glycol, CH2OH, CH2OH. And I'm told that the reaction is first order, so I'm giving a very vague instruction. What is the rate law? So in this case, I'm going to apply a little bit of chemical intuition here. I'm going to say that the rate of CH2 is equal to K times the concentration of CH2 and it's first order, so I'm going to leave it as that. So I was only told that the rate is first order. I wasn't given any information about the different concentrations that come into play. I just picked this concentration and said that it was first order. Why did I do that? So the reason I did this, and this is where you can apply your chemical intuition. So if needed, in this case, you're not given enough information. So this is a good place where you can apply your chemical intuition. So if you were given enough information, then don't second guess whoever gave it to you. If someone gave you not enough information, now you apply your chemical intuition to get a rate law that's reasonable. In this case, the CH2OCH2 compound is reacting with water. So I'm going to assume that the water is present in large excess to CH2OCH2. So I'm going to assume that if there is any concentration dependence on water, that it's buried in this rate constant and that it's essentially constant, at least at this constant, or at least as a function of concentration. And the reason for that is because water is ubiquitous and it's relatively inexpensive compared to other reactant species. So why am I going to do that? I'm going to assume that the concentration of H2O is much greater so the kinetics are controlled much more so by changes in CCH2OCH2 than So again, this is basically, when we're taking rate laws, we basically just want to do something reasonable. The point here is to do a reactor design based on kinetics. If you need a rate law, there's several strategies to get it. Just do something reasonable. Don't make it the problem too hard. And write down what you did. If you make an assumption, just write it down. Okay, let's do one more example. In this case, the reaction 2A plus B goes to C is first order in B and minus second order in A. What is the rate law? So the rate law in this case is minus RA is equal to a rate constant, CB divided by CA squared. So in this case, it's somewhat counterintuitive to what the reaction is because it's non-elementary, but again, I'm being told the kinetics and I'm just going to write those down. So other examples that you'll see in this class, sometimes the rate doesn't follow a power law model. For example, for formula problem 514, which I believe you're going to do at some point in this class, this is the reaction. It's a dehydration reaction of butanol over a catalyst, and the rate law is given to you, so you don't have to derive it. It's given to you like this, where PA is the partial pressure of A is equal to butanol, and Kc is a constant, so specifically Kc is the adsorption equilibrium constant for butanol on the catalyst. In this case, we're used to you're looking at rate laws in terms of concentration. This one's given to you in terms of pressure. This is for a gas phase reaction, so pressure and concentration are related through the ideal gas model. So you could take this expression and sub it into the rate law, and you would get something like this. If that, again, this is your rate law, it's not elementary, it doesn't even follow a power law model, but this is given to you, and when you do your reactor design, you can simply take this expression or this expression depending on, how you set your problem up and what your units are, and just use that as it's given to you. So to drive these points home, some tips: don't overthink the construction of the rate law, just do what the problem's telling you. If you're not given enough information, then make a reasonable assumption and write down what you did.